Let's study recursively defined sequences. One of the most famous ones is the Fibonacci sequence, and it's this sequence here: 1, 1, 2, 3, 5, 8, 13, 21, 34, and so on. And what that is that after you start from the first two terms, 1 and 1, then from then on, to get the next one, you sum up these two, and to get the next one, you sum up the previous two. 1 plus 2 is 3. To get the next one, you sum up the previous two. 2 plus 3 is 5. To get to 8, it's 3 plus 5 is 8. To get to the next one, 5 plus 8 is 13. 8 plus 13 is 21. 21 plus 13, 34, and so on. So to get to the term you want, you sum up the previous two terms. So you have to have some kind of starting point that's different than the general term formula type, because you have to get it launched, and you have to know what your end boundaries are. So if you start with S sub 3, that'll be the previous two, S2 plus S1, say n minus 1 and n minus 2, and that will be 1 plus 1, because that's what was given for those two, which is equal to 2. And then S4 will equal S3 plus S2, the previous two terms. S3 was just figured out to be 2. S2 was given to be 1, so that's equal to 3. And so you can see that the recursively defined sequence is matching up to the Fibonacci. Alright, so you might be interested to know that Fibonacci, right over here, was this guy here, and he lived around 1170 to about 1240 AD, and he came up with this. And then later it was discovered that an approximate general term formula for the Fibonacci, but it's only approximate, there's a approximate sign there, is this here. And if you put that into Y1 on your calculator and do a table, you'll see that every decimal number here rounds off to the Fibonacci number. 1, 1, 2, 3, 5, 8, 13, on and on forever. So that will actually work. And then what's interesting about that, so it's not an actual general end term formula, but it's an approximate. Now this 1 plus square root of 5 over 2 is very interesting. It's the golden ratio, which was a desired ratio for pictures and rectangles. And so that if you had a picture with a width 1 over here and side x, then x to 1, which is a to b, if it was the golden ratio of those sides, it would be satisfying this definition that you can read there. If a and b are two numbers such that the ratio of a plus b to a equals the ratio of a to b, then the golden ratio is a to b. So we're going to solve for this to find out what that actual ratio is that satisfies that definition. And we come over to here. A plus b to a is equal to a divided by b. So if you call a x and b is assumed to be 1, so it's x to 1 is the ratio, then you have this equation, and that results in this one, and that has roots 1 using the quadratic formula, 1 plus or minus square root of 5 over 2, and x is greater than 1 in the picture, so we're going with this one, and that's the golden ratio. Golden ratio shows up in animal shell spirals, and has to do with these boxes that are created here and here and here and there. The sides of those boxes go in a Fibonacci pattern of sides. Last example is find a recursive definition for this sequence. So one of the tricks of the trade is just to write the numbers out and analyze the differences or the ratios. So you would go 5 divided by 1, 14 divided by 5, 30 divided by 14. That doesn't seem to be yielding much, but the differences do. 5 minus 1 is 4, 14 minus 5 is 9, 30 minus 14 is 16, 55 minus 30, 25. And those are squares, perfect squares. So it looks like if you add a perfect square onto the previous number, you get the next number, and if you add the next perfect square onto the previous number, you get the next number. So that's written here in a recursive definition. You add the n squared onto the previous term, and you get the term you're 1. And that's good for n equals 2 on. So you could say that as n greater than or equal to 2, n greater than or equal to 2, and S1 and S1 equals 1. So you have S2 is equal to 2 squared, because you're on the 2 squared, plus the previous, which is S1. So that's 4 plus S1 is 1, so you get the 5. So that checks out. Then S3, that's n equals 3. It's 3 squared, n squared, plus S sub 2, which is the previous term, and that's 9, plus the previous term is 5, gets you to 14, so that's working. Last one, show that the Sn general term satisfies the recursive definition. So here's a general term, and we're supposed to show that it satisfies this recursive definition. So first, using the general term, just so we can see what's happening, if you plug in 2 into the formula, you get 2 times 2 plus 1 divided by 2 is equal to 3 plus 2 is 6 divided by 2 is 3. And if you do that procedure, you'll get these numbers. So that's what the sequence is. Using the recursive definition, it's the previous plus n. So the previous is 1 because S1 was equal to 1 given, plus the n you're on, 2, because your n is 2, is equal to 3. That checks. S3 is the previous term plus your n of 3. That's 3 plus 3, 6, and the S4 checks out. And you should know that this happens to be the sum of the first n integers is what this sequence is defining. Okay, so now we're supposed to prove this though. We're supposed to prove that the general term satisfies the recursive. So if we use the recursive formula, the n times n plus 1 over 2, which is the general term, is supposed to equal the previous term, which is this, plus n. You see it's the previous term because it's the n minus 1 and the n minus 1 previous term. So if you work this all out algebraically, it comes out to this, and that equals up to what you're trying to show. So the two sides are equal. So the general term satisfies the recursive formula.